So in this problem, we're asked to, starting with the function square root of x, or positive square root of x rather is what I should say. Starting with this function, we want to do translations and reflections and get this function. So y equals the negative square root of minus x minus 1. So it's, as I said, it's not a difficult problem, but there are these little areas here I'll show you where it's, there's room to make some mistakes. So I give a hint here. I say, what's the domain of the function? So the idea there is, the domain and range will help us at least verify if we're in the right neighborhood, And we don't do these things purely with just the translations. We're also going to look at the domain and range and maybe plot a few points. That's the full kind of holistic approach to solving a problem like this. So the domain here, so as you know, we have two domain restrictions in general, that we never divide by 0 and we never take the even root of a negative number. So for the domain restriction for this function, I need to check where this expression under the root minus x minus 1 is greater than 0. And so that's the equation here that I've started with. I say set minus x minus 1 greater than or equal to 0, and I want to solve for x. So here what we're going to do is I can just take this negative x and move it to the other side. When we do that, it becomes positive. Okay, so let me do that here. I'm going to make this negative x disappear from the left-hand side. And now let me move it to the other side. Let me make this 0 disappear also, and then I'll replace it with the x. So I took the negative x that was over there and I moved it, and when I move it, the minus sign becomes a positive. So I took the negative x, moved it to the other side. So now I read this equation. It says -1 is greater than or equal to x. And I want you to be able to read the equation in both directions. So if you read it this way, it says -1 is greater than or equal to x. But if we read it the other way, it says x is less than or equal to -1, which is exactly what I've written here. So this is our domain. And so now let's do the transformations. Okay, so whatever function we get, the domain better be x less than -1. And if you look at this, because this is a negative square root, the range here is going to be x less than or equal to 0. So here I'm expecting to see a function with domain x less than -1 and basically below the x-axis. That's what we're expecting to see. So here are the standard transformations, starting with square root of x. So there's my positive square root of x, rather, I should say. There's my positive square root of x. I'm going to replace the x with a minus sign. When we do that, it flips the curve around the y-axis. For positive square root of negative x here, the domain would have to be x less than 0. So it's flipped it around the y-axis. Now, I replace the x with the x plus 1. So right in here, I replaced this x with x plus 1. And the x plus 1 is a left shift. So here, the curve shifts to the left by 1 unit. My very last step now is I put this minus sign on the outside. And that flips the entire curve about the x-axis. So this graph right here, you see where the domain is x is less than -1, and you see the range is less than 0. This graph right here is the graph we're looking for. So now I want to show you some, potentially tricky little mistakes that could happen. So here's one I want you to be careful of. So here, so let me clear this out just so that we can see it fresh. Okay, so here, as before, I start with square root of x, no problem. Positive square root of x, no problem. Then we replace the x with negative x, so that flips it about the y-axis. So far, so good. So now, so let me put an axis here. So now if you look, this next step here, it's very tricky. If we interpret, so now they have a minus x here, then I say minus x minus 1, and there's a minus 1 here. If we interpret this minus 1 as a right shift, typically we interpret, if you do a minus the constant, it's a right shift. The curve shifts to the right here. And you can see the domain is wrong. And then if we do the other, we do this minus sign, it flips underneath, but this is the wrong graph. So right here, this is actually not a right shift. And what's going on there? Well, what's going on is that in our rule, the minus 1 is a right shift only if the variable is just x. Here, the variable isn't just x. The variable has a minus in front of it. This minus sign kind of changes the game. And so that's why you have to be careful here. I can't interpret this minus 1 as a right shift. It would give me that, and that's wrong. So that's one thing to watch out for. And then there was another one I wanted to show you. If you look at this one down here, again, let me clear these out first so we can look at this fresh. And let me throw on an axis. Okay, so let's take a look at this set here now. So as before, we start with positive square root of x, no problem, no problem. So now what I want to do, I replace the x with x plus 1, all right? So x plus 1, this is a left shift. So then it looks like this. And this is at minus 1. So far, so good. So far, so good. Now, I put this minus sign here. We usually interpret the minus sign as a y-axis reflection. So if I take this curve, reflect it about the y-axis, I get this, which now we're in the wrong domain. And then if you do the final reflection below the x-axis, you get this. Again, this is wrong. This graph is wrong. And so what's the problem? The problem is right here, this is actually not a y-axis reflection. What's going on? So what happens, it's kind of sneaky. When this function shifts to the right, our line of reference, our y-axis, which is our line of reference, also moves slightly, moves to the left 1 unit. So this minus sign is actually a reflection about this vertical line, this reference line which shifted to the left. If you do that reflection, then you're in the correct domain. And there's that new reference line. And then if you do the final minus sign, this one right here, that gets you the correct graph below the x-axis. So I'm going to let you think about that. And it's just, I want you to take a look at these two potential mistakes when doing the graph. The other thing we want to talk about in this section is known as the algebra of functions. So what I'd like to start with two functions, f and g, and use those to create new functions, okay? And anytime we talk about functions, it's very important that we keep in mind the domain. So the first definition we're going to need for finding out the domain of combined functions. So given two sets, A and B, the set of all elements belonging to both sets, A and B, is called the intersection of two sets. And we use this notation. A, and then here's the intersection symbol. It's like a horseshoe facing downwards, and the letter B. Okay, so here's how you can think of the intersection. Suppose this right here is set A. So this is my set A. And this right here is set B. So this is my set B. The intersection, by definition, is the overlapping common region. So this section here, where they're overlapping, where they have a common elements, that's the intersection. So it's all of the elements that belong to both of the sets. It's the elements that are common to both. Think about what the word intersection means. When one thing overlaps another, you know, they're intersecting. So here's a very technical math definition that you shouldn't worry about, but I wanted to write down the set definition. So we would read this in math as A intersect B is the set of all elements X such that, so this vertical bar we interpret as the words such that, X is an element of the set A and X is also an element of the set B. So you don't need to worry about this. Really, you should just know that the intersection is the common region. It's the points that belong to both sets. So why do we care about intersections? Because here we can use it to find domains of these new combined functions. So suppose I have a function f of x with domain D1, and I have a second function g of x with a potentially different domain D2. So now what we'd like to do, for example, is add the two functions. So here we define f plus g of x to be f of x plus g of x. So here I think it helps to think of this f plus g as a new letter of the alphabet that we're trying to define. And I'm using the old functions f of x and g of x to create this new function called f plus g of x. So think of f plus g as a new letter of the alphabet. And here we need to know the domain. Anytime we talk about a function, we should talk about the domain. So here for the right-hand side of the equation to make sense, for f of x to make sense, x would have to be in the domain of f. So x has to be in D1. For g of x, for the statement g of x to make sense, x has to be in the domain of g. So x has to be in D2. So at the end of the day, we can conclude that this function f plus g of x, f of x plus g of x, or f plus g of x, will only make sense if x is in the intersection of the domain of f and the domain of g. And in 1 second here, I'll do an example of intersections. It's very easy. You just draw it on the number line and you see where the two regions overlap. I'll show you in 1 second. But here, based on the theory, the domain of f plus g of x has to be the intersection, the common domain, D1 intersect D2. So these are the points that are in the domain of f and also in the domain of g. Again, we can define the difference, f minus g. And you know, again, I would recommend the best thing to do is to think of f minus g as a new letter of the alphabet. And we're trying to define this new letter of the alphabet using these previous two old functions that we have, f of x and g of x. And so this is defined to be f of x minus g of x. And again, the domain is the intersection. Again, x has to be in the domain of f and the domain of g. Then we can define the product of functions. So here we define this new letter called fg of x, which we define as f of x times g of x. And again, the domain has to be all x belonging to the domain of f and the domain of g. That way, both f of x and g of x makes sense. Finally, well, not finally, operation number 4 is division. So we define f over g right here, f over g. Think of that as a new letter as f of x over g of x. And again, for f of x to make sense, x has to be in the domain of f. For g of x to make sense, x has to be in the domain of g. So we have x is in the intersection, but because there's a denominator, we have an extra requirement. Remember, we always have to make sure the denominator is not 0. So any x value that's in the domain of f and in the domain of g that makes the denominator 0 is left out of the domain. And I'll show you an example here in 1 second, okay? So the fifth operation is known as function composition. So function composition comes from a very simple idea. As you know, a function is an input-output machine. So the idea is if you have two functions, why don't we use one of the functions as the input for the other function? And that's called function composition, okay? So starting out with two functions, f and g, I define the composition of f with g. So this is composition of f and g, or f composed with g, which is different from g composed with f. So here's the notation. We write f little circle g. So this notation is you would read as f composed with g, and then the definition is given on the other side. The definition is f composed with g of x is defined to be f of g of x. And what you should see is we took g of x and made it the input for the function f of x. And so now the very next question we should ask is, what's the domain? Okay, so it's important here to follow the journey of the variable x. Let's think about what x goes through. First, x has to go into the function g. First, x is an input for g. So x has to be in the domain of g. Then g becomes the input to the function f. That's how you get f of g of x. So x has to be in the domain of g, but g of x has to be in the domain of f. So remember, for this to make sense, f of g of x has to be in the domain of f. So I'm looking for all x values that are in the domain of g, for which g of x will also be in the domain of f. Okay, and I'll show you an example here. It's a little harder to describe with words. When you actually do the math, it's a lot easier. With the math, you can just do the math. Here we're thinking about it conceptually, so to talk about it in terms of words is a little difficult. So we're looking for all real numbers x, such that x is in the domain of g, so g of x would make sense, and g of x is in the domain of f of x. Okay, so let me show you an example. So we start with two functions, the positive square root of x right here, and g of x is the positive square root of 1 minus x. We want the sum f plus g of x, and more importantly, what's the domain? Okay, the sum, this part, finding the sum is easy. Figuring out the domain sometimes requires a little bit of more work, okay? So first, the domain of positive square root of x is x has to be greater than or equal to 0. So 0 to infinity, which we can write in interval notation this way. That interval notation means x is greater than or equal to 0 and strictly less than infinity. And for the positive square root of 1 minus x, here, for the domain, remember, we need here 1 minus x to be greater than or equal to 0. So I set up the equation. I say we need 1 minus x to be greater than or equal to 0. Take this minus x and move it to the other side. Then you get x is less than or equal to 1. And that's what I've written here. Remember, I want you to get used to reading the equations in both directions. Read it this way as well as the other way. So I wrote this equation the other way, x less than or equal to 1. Okay, so now if you look on a number line, so let me do a number line. If you look on a number line, one of our domains, so let me put 0 in here somewhere. So here's 0. Here's 1. So one of our domains is greater than or equal to 0. So greater than or equal to 0. So here, That's the domain for our positive square root of x. And the other domain is less than or equal to 1. So this is the other domain. And so now I'm looking for the common overlapping region. And you can see the region where they overlap is right here. That's the intersection. That's the common region. So I say f plus g of x equals positive square root of x plus positive square root of 1 minus x. And the domain is d1 intersect d2. d1 is the domain of the positive square root of x, which is 0 to infinity, intersect the domain of positive square root of 1 minus x, which is negative infinity to 1. And as we saw on the number line, if here's 0 to infinity, and here is negative infinity to 1, you can see the common region when you overlap them. So this right here is 0. This right here is 0. If you overlap the common region, we get 0, 1. And so this is my final answer down here. I need to write the function and the domain. If you don't specify the domain, the answer is incorrect. That's my final answer with the domain. This part is important. For the second example is related. It's the same functions, but now we want the quotient, not the quotient, not the sum. So as before, f over g of x by definition is f of x over g of x. So finding the function is not the hard part. What we should do is think about the domain. That's always kind of the part that requires a little bit more thoughtfulness. As before, I'm going to take the domain of f, intersect with the domain of g, I get 0, 1. But in this case, because there's a denominator, we have an extra step that we need to do. I cannot forget that there's a denominator. So I need to now make sure I remove any numbers from 0, 1 that'll make the denominator 0. So let me check. The denominator is 0 when positive square root of 1 minus x is 0. That happens when x is equal to 1. So x equal to 1, I have to remove from the domain. I cannot include it here. Cannot include x equal to 1. I have to remove that. So here's my final answer. So we exclude x equal to 1. So the function looks like positive square root of x over positive square root of 1 minus x. If you stop here, you haven't finished the problem and it's incorrect. We have to include the domain. And we say where x is in closed 0 to open interval 1. So x greater than or equal to 0, but strictly less than 1. Let's do a composition problem. Here we have f of x is equal to x squared. G of x is equal to, so here's f of x as x squared. G of x is equal to the positive square root of x. And so now we're asked to find f composed with g and g composed with f. And I'll show you these two aren't the same. F composed with G and G composed with in general are not the same. And in this example are not the same. I'll show you. Even though they look very similar, but they're actually not the same. It's kind of slightly tricky. So first, let's figure out the domain. The domain of x squared is all reals. It's a polynomial, so it's very well behaved. The domain of positive square root of x, as you know, we need x here to be greater than or equal to 0. So the domain is greater than or equal to 0. Okay, so now that we know the domain, let's work out the compositions. Here we go. F composed with g of x. So you need to know this notation and you need to know the definition. This just means take g and put it inside of f. So here's f of g of x. So now I'm going to replace g of x with its definition. You remember g of x here is the positive square root of x. So at this very stage, for this math to make sense, we already have a restriction. Whatever the domain is, I need to have x greater than or equal to 0 so that this very first step even makes sense. I cannot write down this expression. I cannot write down f of the positive square root of x unless x is greater than or equal to 0. So whatever my final answer is, I'm going to have to figure out what it actually looks like. I'm going to have to intersect with x greater than 0. So now I take positive square root of x and put it into the function f. F is just the squaring function. So we take positive square root of x and square it. And so you get x, but you have to be careful. The domain, I have to calculate the domain. The domain of x by itself is R. But we also have this restriction. So here you see I'm doing an intersection. I'm saying here's my restriction intersected with the domain of the final answer. So now I've found the domain of the composition. So here, my final answer would look like this. And if you leave out the domain part, then it's wrong. This part is crucial, where I say x greater than or equal to 0. So even though this function x is defined for all r, this part is not. And so that's why I'm intersecting here. You see, I'm intersecting the domain of x with the restriction. So that's how we get that domain. So look at the next functions. Here, I want to do g composed with f, right? So here, it's the composition is the other way, g composed with f. So that's g of f of x. So now f of x is the input to the function g. So look, if I replace f of x is just x squared, right, from up here. F of x is just x squared. X squared has no domain restriction. So here, x squared, the domain here is all reals, okay? So now plug it into g. Remember, g is this positive square root function up here. So plug it into g. So now I'm taking the positive square root of x squared. So be really careful. Here's what most people would write, okay? Most students at this point would write the following, and let me show you what most students would write. Most students would now say, and it's a very natural mistake to make, but a mistake nonetheless. Most folks would say this positive square root of x squared is x. And this would be wrong. This would be wrong. So
it is plus or minus x.
No, it isn't plus or minus. So this thing here on the left side, positive square root of x squared is always positive. It's the positive root. So the right-hand side, this has to also always be positive. So the positive square root of x squared is actually the absolute value of x, because both sides have to be positive. This has to be positive, and this has to be positive. If I leave off the absolute value bars, if I just write this, then x could be negative. Here, the domain is all reals. So that's one thing we have to remember. At this stage, the domain here is all real numbers. Here, under the square root, there's no problem. Here, because we're squaring, we know we're never going to take the even root of a negative number. So for this problem, it's okay to send any x value, positive or negative, because it'll first get squared. So here, the final and correct answer for this problem would be to say f composed with g is the positive square root of x squared, which is the absolute value of x, where x is allowed to be any real number. That would be the final and correct answer. In general, it's not true that the positive square root of x squared is equal to x. This equation is only true when x is positive. If x is greater than or equal to 0, then no problem. then yes, this equation is true. Then this is equality. But when x is negative, that's not true. So you have to be careful. We'll come back to this point a couple of times. Okay, remember, this is not the square root, it's the positive square root. The left-hand side here has to always be positive. So the right-hand side here has to always be positive. Okay, so I'm gonna let you think about that. Okay, folks, this ends section 1.2. So now I'm gonna switch over to the slides for section 1.3, which I emailed you on Saturday. And so here's the section 1.3. It's the informal definition of the limit. So we start talking about limits. So before I talk about limits, I want to talk about some language. There's a phrase we use all the time in math called if and only if, and it's a technical phrase. It's very important that you realize we're using English in mathematics in a very technical way. Every word has a very specific definition. Okay, so if and only if is a technical phrase that's used in mathematics. So we need some background. So first of all, a proposition is what's known as a declarative statement that has what's called a truth value. So there's two things happening here. We have the idea of a proposition, and then we have the idea of a proposition having truth values. Okay, so in math, we're only interested, basically the goal of math, this pretty much sums up most of mathematics, if not all of mathematics. In math, we seek to determine the truth values of propositions. So we look at propositions that have truth values, like today is Wednesday. That's either true or false. We avoid things that don't have a definite truth value, like a question, what time is it? That's neither true or false. So we don't talk about that in math. Or commands, sit down, stand up. Those are neither true or false. So those are not the types of propositions we look at in math. We look at propositions that are either true or false. Okay, so for example here's an example of two propositions. So you have proposition P is the proposition that there are 4 Three Stooges. And proposition Q is the proposition that 1 + 1 = 1. So these propositions have a truth value. They're either true or false. We know proposition Q is false, 1 + 1 is 2, and we know proposition P is true. There are, in fact, 4 Three Stooges, right? Larry, Moe, Curly, and Shemp. So, of course, in math, in calculus specifically, the propositions we look at are of a mathematical nature, right? Now, there's a very special type of proposition called an implication. So here now, I want to talk about this very special type of proposition known as an implication. An implication is basically what's known as a conditional statement or an if-then statement. So an implication is a statement of the form, if P is true, then Q is true. Or another way to say it is P implies Q, or in math, we like to use symbols a lot instead of words. So the way to write an implication would be P and then this double arrow to Q. I would read that in the shaded box as P implies Q, or if P, then Q. And in math, we're interested in determining whether any given implication is true or false. So here's an example of an implication that's true. If x is non-zero, then x squared is positive. If you want to write that in math notation, you could write it this way. It's the same exact thing. I would read what's in the red box as if x is non-zero, then x squared is positive. And so here what we have, example of two things. One, an implication, and two, an implication that's actually true, right? If you look at the implication above, if I say, for example, if I say, if it's Monday today, then 1 + 1 = 1. That is an implication, but it's not true at all. I mean, that's an implication that's completely false, if not bordering on just nonsense, right? So here's what I finally want to define, this phrase known as if and only if. So the proposition if and only if, this is the same as saying P implies Q and, so if and only if gives us 2 for 1, and Q implies P. So we only say P if and only if Q if the implication goes both ways. And this is known as a by implication. And we use this double-headed arrow instead of the single-headed arrow to indicate the by implication. So these are all the same. You can say P if and only if Q, or you can write P in the double-headed arrow. So in mathematics, if it is true that P implies Q and Q implies P, if both those statements are true, then we just write this. Sometimes the phrase if and only if is abbreviated as IFF. That's the same as if and only if. Okay, so I will use this phrase if and only if now in the next slides, and you'll see it, you know, forever in every math class that you take from here on in. If you've already seen it, I'm sure, but now you'll definitely see it in every math class you ever take. So here's an example of a by implication that's true. So there's two things. This is a biconditional statement. It goes both ways, and it's true. So the statement P is X is not equal to 0. That's the statement P. If and only if Q is the statement X squared is greater than or equal to 0. So to check whether this statement is true, you know, remember, when I see if and only if, I know that's a technical word. I know it's being used in a technical sense. So I ask myself, if X is not equal to 0, is it true that X squared is greater than 0? Yes, that's true. Then I ask myself, if X squared is greater than 0, is it true that X is not equal to 0? Yes, that's true. So here, this by implication is a true by implication, or a true biconditional statement. So it's really important to interpret this statement, the P with the double-headed arrow, or P if and only if Q, as saying this. So these two things are the same. Okay, so let's talk about limits. So let's talk about one-sided limits. So here we've got a function f of x, and we're making x closer and closer to a, but using values of x that are smaller than a. And now if the y values, so here for each of these x values, we're looking to see what the y values are doing. And as we get closer and closer to a, in this picture, you can see the y values are approaching L. As x goes to a, y goes to L. So in this case, we write the limit of f of x as x approaches a, and we put a little minus sign here to indicate we're approaching a with numbers smaller than a. So this is approaching a from the left. So here, x is on the left side of a, right? Or here, I've used the biconditional, a similar exact same notation. Another way to write the left side limit is this, that the value of f of x approaches the finite number L as x approaches a from the left, using values of x smaller than a. And we can also take a limit from the right. So now I'm looking at an x value that's bigger than a, and making this smaller and smaller, getting closer and closer to a. So what I'm doing is I'm going up here, and we're looking here, and we're seeing where are the y values going. And in this case, you can see as x gets closer and closer to a, the y values get closer and closer to this number r, which is a finite number. In this case, we can say that f of x approaches r as x approaches a from the right, and we can use this notation. We can say that the limit of f of x as x approaches a from the right, that's what this plus symbol tells me, is equal to r. You know, this other notation here is exactly the same concept. It's just a different way of writing the same thing. That's why I have my biconditional here, to indicate these are the same. If you write one thing, that implies the other, and if you write the other thing, that implies, you know, the former. So these are just alternate notations that you might see in the book. You know, they might want one time they might write the limit in this form, and then one time they might write the limit in this form, but they're the same. Now, here in this picture, you see the limit from the left does not equal the limit from the right here in this final picture here. Oops. So when the limit is equal, something special happens. So here you see the limit from the left does not equal the limit from the right. But if the limit from the left does equal the limit from the right, then the two one-sided limits together are called a two-sided limit, or sometimes just a limit. So now we have the idea of a two-sided limit. You know, here I think there's a lot of potential for confusion. A lot of folks just use the phrase limit when they mean two-sided limit. So I think it's always important to remember when we say limit, we mean a two-sided limit. And for a two-sided limit to exist, we have to check the one-sided limits. So here, if the limit from the left is equal to the finite number L, and the limit from the right is equal to the same finite number L, then we can say the two-sided limit, or just limit, of f of x as x approaches a equals L. So here, when we say x approaches a without specifying, this means both the left and the right. That's why it's a two-sided limit. So here, you know, and we say that f of x approaches L as x approaches a. We don't say from the left or the right. When we just say x approaches a, we mean from both sides. So here, this implicitly means from the left and the right. It's, you know, we don't have to specify here. This is a two-sided limit. And here, in all three pictures, the limit of f of x as x approaches a equals L. Okay, but all three pictures are not the same. In the first picture, f of a is not defined. The function is not defined at a, but the limit is. The limit from the left and the limit from the right are approaching L. In the second figure, figure B, f of x is defined, but it's not defined to be the same as the limit. So here's f of a is defined. So here's f of a, the value of the function, but here's the value of the limit. And you see they're not equal. And that's okay. In this case, the limit exists and is not equal to the function, which is fine. In the first case, the limit existed and the function was undefined at the point, which is, you know, which is totally fine. There's just different options, different possibilities. The third case is kind of like maybe the best case scenario, you know, where the function value and the limit coincide. So the function value is right here, and the value of the limit is also the same as right there. So in this case, the limit exists and is equal to the function at the point. So when this third case happens, a very special property has been achieved at the point. We say the function is continuous at the point. If this limit down here is true, if the limit of the function as x approaches a is equal to f of a, then we say the function is continuous, and that'll be very important. And we'll talk about that, you know, next time. That'll be the topic of the next lecture. So here's the formal definition of the limit, or more appropriately, the two-sided limit. So we say the limit of f of x as x approaches a equals L, if and only if the limit of f of x as x approaches a from the left equals L, and the limit as x approaches a from the right of f of x also equals L, where L here is a finite number. When the limit exists, another word we use for the limit existing is that it converges. And remember, the only way a limit can exist is if it equals some limit L, where L is a finite number. The limit equals plus or minus infinity, that limit does not exist. Plus and minus infinity aren't numbers, they're concepts. So if the limit does not exist, we use this other word, diverges. So you can either use the word diverges or you can say does not exist. Or if the limit does exist, that is if the limit equals a finite number, then you can say the limit exists, or you can say the limit converges. Those are just two different terminologies for the same concept. So let me do an example here. Let me finish this final example, and then I'll stop here. We've just got about 5 minutes. So here we're given a piecewise defined function, and we're asked to find a couple of things. Okay, so let's just read the question first here. So for number 1, we're asked to find the limit of f of x as x approaches 1 from the left. Then we're asked to find the limit of f of x as x approaches 1 from the right. Then we're asked to find the two-sided limit. Okay, so I want you to, these are 3 different kinds of limits here, but they're all related. In number 2, we're asked to find the limit of f of x as x approaches 2. What I want you to say is we're asked to find the two-sided limit of f of x as x approaches 2. Number 3, we want the two-sided limit of f of x as x approaches 3. Finally, I want the function values, f of 1, f of 2, and f of 3. So let's do number 1. So for number 1, for this limit, when we say x is approaching 1 from the left, what we're saying is x is very close to 1, but less than. So this is exactly this scenario right here. Very close to 1, but less than 1. And so in this case, the function I'm going to use is 3x. I'm going to take 3x, and the typical way we do it is we make a table, and I'm going to plug in numbers closer and closer to 1 into the function 3x, but that are less than 1. And we're only going to do this once because the human brain can sort of predict what's happening once it sees the pattern. So here you can see I've got numbers to the right of 1. These the less than 1. So these are all numbers to the right of 1, but approaching 1, getting bigger and bigger, closer to 1. And I'm plugging each of those into the function. I'm not actually calculating the value. I'm just asking, where is this pattern going to go? 3 times 0.9, 3 times 0.999, 3 times 0.99999. Eventually, it's going to go to 3 times 1. And so I can predict the limit of f of x as x approaches 1 from the left is 3. So that's what I've written here. And this might look slightly different from your slide because I added here. Here I plugged in. So here for f of x, x is less than 1, but very close to the left. X is less than 1, but very close. So the function I plug in is 3x. And then you plug in points closer and closer to 1 from the left and predict what's going to happen. For the other limit, here when we say x approaching 1 from the right, that means x is greater than 1, but very close. So for that second limit, x is greater than 1, but very close, I'm going to use this as the function in the limit. And that's what I have here. And now you plug in values here larger than 1, but that get closer and closer to 1. Eventually, this will approach 2 plus 1 squared, which is just 3. And here I see the limit from the left is 3. The limit from the right is 3. So I can conclude the two-sided limit must also be 3, because that's the definition. For the two-sided limit to be equal to 3, I need the limit from the left to equal 3, and I need the limit from the right to equal 3. And so here for this function, we've been able to verify that by plugging in points. And I wanted to highlight with this first part of this example, the relationship between the two-sided limits and the one-sided limits. How in this case, I had to do the one-sided limits first before I could figure out whether the two-sided limit was there. And if these two one-sided limits were not equal, then the two-sided limit would not exist. So folks, this is my time, so I'm going to stop right here. I'm going to pick it up right here next time. Thank you, everybody, for your time.